Okay, we're going to carry on with lecture 1, which really covers the topic of strength, stiffness, and stability, and what is structural engineering. We're going to do a few quick kind of reviews of basic math as well. It's not going to be a long lecture. We'll ease into this, and then next week we'll pick up on we'll start into kind of more in-depth topics. So let's talk about what structural engineering is. Structural engineering is a field of engineering dealing with analysis and design that supports and resists loads. So that means we have a few things going on there. We have to be able to figure out what the loads are that are acting on it. So something is happening to the object. We have to figure out what's happening within the object to be able to support those loads. And then it has to come out of that object in reactions somewhere. So we have to figure out how it gets out of the object into the next thing. So if it was a beam, for example, we have to figure out what the loads are acting on the system, how the loads get to the beam, which is probably deck spanning onto a beam. And then we have to figure out how the beam behaves. Can it carry those loads? Is it strong enough to carry those loads? And then we have to figure out how the loads get out of the beam, which it would probably be going into two columns at either end. And can the connection between those handle the loads that are in that location? If it was the building overall, we have to get those loads out into the soil somehow, into the ground. So we have to look at several steps throughout the building and the building as a whole. So I just kind of want to briefly talk about design as a concept and whose roles are what, and this kind of ties back into why you need an engineer even though you're studying to be architects. So any kind of design issue has somebody defining a problem. That doesn't mean creating a problem, that means defining the problem, because everything is always about trying to solve problems. So we need to define the problem, and then we need to solve the problem. And depending on what stage of the project we're at, we change roles in that. So the very first round, the owner comes to you with a problem. Now, when I say problem, I mean that very loosely. Their problem is they have a piece of land and they want to put a 10-story commercial building on it. You're the architect, and it's your job to find the solution to that problem. There might be other problems. Obviously, there's going to be more problems in it. So you start coming up with a solution. You create a set of preliminary layouts and preliminary sizes. And then you involve the engineer. So your problem now, as the architect, you're defining the problem, and you're defining your problem as, I have these drawings, I need to make sure that it works. The engineer solves the problem by showing you what makes it work. And then the engineer's defining the problem by saying, here, I have created this structural element that you need to build. And the contractor's solution is to build that engineered system. So, and there's more roles within this. It kind of changes around. Sometimes it goes back and forth, but we always have a defined problem and a problem solution. But you can't solve the problem until you've defined the problem. So sometimes you can come to an engineer with a question, and what they're really trying to say, they're not trying to say they can't solve the problem. They're saying they don't understand what the problem is. So sometimes that is the issue and miscommunication between architects and engineers as well. So let's talk about design let's talk about it as a 3-step process. So a very broad idea of how design happens, whether it's an architect or an engineer. And then we'll go into like a deeper look at it. So the 3-step process, or how I like to think about it, the first thing you do is understand the precedents. Now, I know you guys spend a lot of time looking at precedents, but you spend a lot of time looking at the craziest, most abstract precedents, which is perfect. You guys are going to U of T because you're one of the best design schools in North America. But part of that means you're not looking at the things that are normal. So I'm not talking about the crazy out there precedents that you guys are going to spend a lot of time looking at in studio classes. I'm talking about understand the actual precedents. If you're going to design a rink, you're going to go look at rinks that are already built. You're going to find drawings for rinks that are already built. And you're going to see that there's 2 or 3 systems that work really well. Not because they have no imagination, but because they are the cheapest system with the materials that are available, with whatever the problem that the owner has defined. So if they have defined money at all costs, being preserved, saving as much money as possible, your set of criteria is going to be different from an owner who says, I want a gem of a building, spare no cost on building this building. You still have a problem and you still have to solve it. You have a problem defined and you still have to solve it. But the context in which you can do that has changed. So first step, understand the precedent, the normal, basic, boring type of that building. You need to understand that. When all or bits of the precedent doesn't work, that's when you start to refine. If you have a pop-up in your rink and it doesn't meet the normal criteria, well, maybe there you need to start to think outside of the box. You need to either retool it or look at a different precedent that you can combine with that. And then step 3, innovation is amazing. But innovating when it's not necessary is just a waste of time and money. When there is a good, cheap solution that doesn't cause any other problems, your smartest bet is to use that. I do not want to limit innovation at all. I want innovation. Innovation is amazing. But if all of the precedents work and there's no other problem, there's no need to innovate. You have a system that works. When those things don't work, now it's time to start talking about innovation. Okay, let's look at it. That was kind of abstract. That was more of a thought process. Let's talk about it more as how we actually go about designing these systems and how the relationships work. So the first thing that happens is the owner comes to the architect and says, build me this building, and they give you some criteria. So the first thing is step 1, the architect selects the system, whether it's wood or concrete or steel, and they figure out a general building and a general layout. Step 2 is still usually the architect. Sometimes, if it's a high enough end project, maybe it's a competition, you might already have an engineer on board, but it is unusual to have an engineer on board at step 2. So that's early design work, kind of preliminary design development, or maybe even schematic design stage of a project. You probably create a set of drawings that you produce and give to the client using sizing guidelines or rule of thumb. And that's what would tell you what your preliminary sizes are for your building and your building layout. After that, you go to the engineer and say, okay, here, I've done it. I have an idea of what I think the sizes are. Now you take it and tell me if I'm right. So now the engineer will go through and figure out the loads on the building and analyze every member and come back and say, they'll figure out all the loads acting on the building. So the engineer does this stage, but sometimes the architect needs to weigh in. A good example I always like to give is the Goldring Center for High Performance Sports. Obviously, I can go to the building code and figure out what all the loads are in it. One of the unique things about that building is that on the 4th floor, there was an MRI unit. Now, if you don't know what an MRI is, it's a magnetic resonance imaging system. It is highly sensitive to vibration. In fact, in the manual, it typically says we won't warranty it unless it's in the basement. So you have to work really closely with them to get them, you have to satisfy their criteria to get them to validate their warranty. So that was on the 4th floor. On the 2nd floor, on the 3rd floor, we had an Olympic weightlifting facility. If you don't know what that is, if you know those guys that hoist up the big, huge bars over their head, hold it for a few seconds, and then throw it down on the floor, and they bounce. So we're talking a ton of weight. We had that on the 3rd floor. Now, in the Goldring Center for High Performance Sports, the 3rd floor was hung from the underside of the 4th floor. So here we have this high vibration thing with people throwing big weights on the floor, hung from the underside of a floor, supporting a thing that's highly sensitive to vibration loads. that is outside. I wouldn't be able to just look at the drawings and know that that was a unique criteria. I wouldn't know that that X on the drawing was the MRI unit. The architect needs to know when something is unusual. It's not your job to figure out what all the loads are, but it is your job to know when something is unusual. So you should have an idea of what regular loads are so that you can identify when something's unusual, because you need to then communicate that to the engineer. The fourth step would pretty much be the engineer alone. That's where they say, okay, we've got all these loads. We're going to check and see what they do to every member, every connection, and every system within the building. And then the engineer says, okay, maybe looking at what the architect has done for the sizing guidelines and says, what members are stable, strong enough, and stiff enough to support all of those loads we just figured out in the last stage. And then the engineer goes back to the architect and says, here's what we had, and then we have to kind of go back to the beginning, because obviously not everything's going to work. Some of the sizes of beams might be too big to fit in the ceiling plenum, or you have a stair there and people might bump their head, or you need to shift a column because there's a door there. So we go through the process several times throughout this design process. So structural design to an architect, you'll need to know how to pick the best system and the best layout and the appropriate sizes. So that's again using the sizing guidelines or coming up with a preliminary set of sizes for your drawing. Now, when I say best, I mean best within the criteria that you have. Like I said, you might have an owner who wants the bare minimum of a building, or you might have an owner who wants the most elaborate, most fancy building they can possibly have. So what is best might change between those two contexts. So you have to understand what best means for that. My computer's starting to freak out and vibrate. Okay, I'm going to figure that out, and I will come back and keep recording this.